Turn on any tap in your house and water comes out under real pressure, enough to spray, to fill a kettle in seconds, to feed a shower 2 floors up. And there is no pump anywhere in your house doing that. So where does the push actually come from? I'm Alex, and this is Unseen Systems. Let's follow the water backward and find out. Here is the strange part. The water company's pumps might be miles away and switched off right now. Yet the moment you open the valve, the pressure is already there, waiting. It never needs priming, it never runs down between uses. Something is holding it ready every second of the day, whether you use it or not. Follow the pipe back out of your house under the street, and it leads to something you have probably driven past 1,000 times without a second thought. A tank of water standing high in the air. And notice where they put it, on the tallest legs in town or up on the highest hill nearby. That is not for looks. The height is the entire point. And that height is the whole answer. The water in that tank is sitting maybe 130 feet above your tap. The exact numbers change from town to town, but the rule underneath never does. Gravity pulls down on that water, and that weight has to go somewhere. It goes into the pipes as pressure. The rule is simple, and it never changes. Every single foot of height adds about 0.43 pounds per square inch. Where does that number come from? A block of water 1 foot on each side weighs about 62 pounds, and it is resting on 144 square inches. Divide it out, and you get 0.43 psi for every foot of depth. Stack up 130 feet of water, and you get roughly 56 psi at the bottom, right in the normal household range. So nothing in your house pumps the water. The utility raised it hours ago, and gravity has been pressing it back down ever since. The tank does the pushing for free day and night. Now zoom out to the whole city. It starts at the treatment plant, where water is cleaned, and a powerful pump gives it a shove. This is the one place a big pump really does the heavy work. But the pump's job is not to push water all the way to your house. Its job is to lift water up into the tower and keep that tank full. Once the water is up there, the pump is done. From the tank, the whole town is fed by gravity through a network of buried mains. The pump lifts, gravity delivers. And there is a lot of water up there. A typical tower holds anywhere from 100,000 to 1,000,000 gallons, often about a full day's supply for the neighborhood it serves. That reserve is what quietly rides out the morning rush, a house fire pulling hard on a hydrant, or a power cut lasting hours. On a hill, though, one pressure cannot fit everyone. Down in the valley, the water arrives too hard, over 100 psi, so a reducer valve trims it back down. Up on the ridge, it arrives too weak, so a booster pump lifts it back into range. Cities carve themselves into pressure zones for exactly this reason. One hilly utility in Reno runs over 300 separate zones. Now the part that is easy to miss. Why store the water up high at all, instead of just running pumps around the clock? Because a city's water use is wildly uneven. In the morning and the evening, everyone showers and cooks at once, and demand can spike to 5 times the daily average. If the pumps had to meet that peak directly, you would need enormous pumps, plus the pipes and power to match, all sitting idle most of the day. Instead, the tower works like a battery. Small, cheap pumps run steadily, often overnight when electricity is cheapest, slowly filling the tank. Then the tank, not the pumps, covers the daytime rush. The pump only ever has to keep up with the average, and the height covers the spikes. It buys one more thing that is easy to overlook: resilience. When a storm knocks the power out and the pumps stop, the tower does not care. All its energy is already stored as height, and gravity keeps the taps and the fire hydrants flowing until the pumps come back. Back at your house, the water crosses one last stretch. It leaves the street main, passes a buried curb valve, and comes through the meter that measures every gallon you use. Then it usually meets one small but important device, a pressure reducer. In many neighborhoods, the street pressure is actually too high for household plumbing, strong enough to hammer pipes and burst appliance hoses over time. So the reducer trims it to a safe level. Plumbing codes cap the house near 80 psi, and the reducer holds it there. It is really just a spring, quietly pushing back against the water all day, every day. Codes even ask for a small expansion tank downstream of it, because once the reducer closes off the street, heated water in your pipes has nowhere to expand, and the pressure would otherwise creep up on its own. And the same height rule from the tower runs in reverse inside your walls. Every floor you climb costs you about 4.3 psi. That is why the top floor shower is weaker than the kitchen tap, and why tall buildings cannot run on street pressure at all. They need their own booster pumps or a tank on the roof. There is one more reason all this pressure matters, and it only becomes obvious when it disappears. A healthy water main is always pushing outward. 40 to 80 psi presses on the pipe walls from the inside all the time, and that outward push is quietly doing a second job. It is a seal. Buried mains sit in wet, dirty soil, and they are not perfectly tight. But as long as the water is pressing out, nothing can press in. But when a main breaks, or a blackout stops the pumps, and the pressure falls below about 20 psi, that seal can fail. The flow can even reverse, and soil, groundwater, and bacteria around the break get siphoned in through the crack. Here is how the Environmental Protection Agency itself puts it.
Loss of pressure in a drinking water distribution system may cause a net movement of water from outside the pipe to the inside, through cracks, breaks, or joints.
That is why, after a big water main break, the city tells you to boil your water for a day or two. The pressure was never just for your shower. It was a barrier keeping the water clean the entire way to your tap. Lose the height, and you lose the seal. And here is the part that is easy to miss. The interesting thing about your water pressure is not that it is strong enough for a shower. It is that the very same push is quietly doing a second job the entire time, sealing the pipe that keeps the water clean, because the moment the height is gone, so is that barrier. So here is the whole thing in a single line. The pressure in your kitchen is not a product the utility makes and ships to you. It is a byproduct of a hill and a tank. Next time you fill a glass, picture the water level it is actually falling from, a surface standing 100-odd feet above your head. There is no pump in your house, just height and the patient, unpaid pull of gravity. That's unseen systems. Keep an eye on the systems quietly holding your day together, my dear engineering fans, and I'll see you at the next one.